Brief explanation of hybridization. If we take an s orbital and we hybridize it with 3 p orbitals, that was the one we talked about in lecture, right? And we end up with sp3. We get the same number of hybrid orbitals as atomic orbitals that we started with. So this was taking s and 3p orbitals, there's the s and the p, and hybridizing those, we get 1, 2, 3, 4 sp3 hybrid orbitals. We okay on that? So what if, instead of using all 3 of the p orbitals, what if we just took 2 of them? So we're going to use 2 of those and the s. What do you think we would call that? We call that sp2. And then what we're going to end up with is we're going to end up with 3 sp2 orbitals, and then this guy just stays unchanged. So that's just a p orbital. I believe that the book is going to talk about this more later, and what we're seeing on the worksheet is the disconnect between the worksheets, which were written by someone else, and the textbook, and hopefully we'll be able to avoid problems like this in the future. So if we have 3 hybrid orbitals, how are they going to arrange themselves in space? How do 3 things get away from each other? They make a triangle, right? And we're going to have 3 sigma bonds here. Somebody want to open that? Maybe just stick the chair in the door or something. Thanks. Hopefully it won't be too loud. I didn't think to go unlock that door. So these 3 orbitals hybridize to make 3 equivalent sp2 hybrid orbitals. They're going to arrange themselves in that trigonal planar form. Well, that's not very good. And then this p orbital is left out. Okay, that's available to make a pi bond. We haven't really talked about pi bonds yet. But if you see a compound in which the central atom has 3 electron groups, it's going to be sp2 hybridized. So in that worksheet, they're having you draw Lewis diagrams and predict the shapes. And then at the end, they're asking you for the hybridization. So the way you identify that is you look at the central atom. Say we have something like this. And here, the central atom has 3 electron groups, is how we did it in Vesper theory. The way we get 3 equivalent electron groups is by using sp2 hybridization. If there's 4 groups, it's sp4. If there's 2 groups, what do you think it'll be? sp. Okay? Does that help? Yeah. We haven't really covered this in the book. My style as an instructor, I like to teach to the book. I think it's less confusing. I was thrown into this at the last minute, and so out of desperation, I used these worksheets without examining them carefully enough to realize that this wasn't lining up with the book. So my apologies about that. Any questions about the hybrid orbitals? So when you're looking at a structure, the way you identify the hybridization is you look to see how many electron groups are around that particular atom. And each individual atom could have a different hybridization. Let's see if I can get back to, yeah. So on this problem number 36, it's pointing to this carbon atom. Now, you have to be careful with these line drawings because there may be some hydrogens involved, right? So you might want to write this out in a more expanded form. So we've got the carbon and a carbon and a carbon, and then we've got this guy in the middle. This is the one they're pointing at. And he's got a double bond to another carbon. There's a carbon up here and a carbon over there. Just drawing the carbon backbone. There's 1, 2, 3, 4, 5 in a row. 1, 2, 3, 4, 5 in a row. There's a double bond in here. That's these two guys right here. This carbon has another carbon attached. This is the line sticking up. This carbon has another carbon attached, the line sticking up. So this is the skeleton. You can't forget the hydrogen atoms. So I'll make this guy red that we're looking at. We need to make sure that we account for all the atoms bonded to him. The hydrogens are not shown in this structure. Is that red carbon going to have any hydrogens bonded to it? How many? 1. How do we know that? It needs 4 bonds, right? It's got the double bond here, that's 2 bonds, and a single here, that's 3. It needs another bond, and the other bond will be with hydrogen. So then we look at this carbon and we ask ourselves, how many electron groups? Not how many bonds, but how many electron groups?
8.
There's 8 valence electrons. But we're thinking in terms of Vesper theory when we're talking about electron groups. So a single bond is a group, a double bond is a group, a triple bond is one group, a lone pair is a group. And so this guy has 3 groups, these 2 single bonds and the double bond. So 3 groups would be what hybridization? Sp2. Okay, so there, I gave you one. So Sp2, if we were going to put an exponent, it looks like an exponent. If we're going to put a superscript on the S, what would it be? When we just write the S, how many S's are we referring to? 1. And the P2 means there's 2 P's. So it would be S1, P2, but we just don't write the ones. 1 plus 2 is 3. When you have an Sp2 hybrid orbitals, there's 3 of them. They're equivalent. And if you have 3 groups, you have Sp2 hybridization. Yes?
So if there wasn't a double bond, though, it would be 4.
Mm-hmm.
But anytime there's a double bond, so if there was 2 double bonds, then it would just be
2. If you had 2 double bonds, if you had carbon like this, like it does this in carbon dioxide, we look at this and we see, oh, there's a double bond, that's 1 group, here's another group, 2 groups. So Sp, because this is 1 S and 1 P, and together those add up to 2. You're going to get 2 orbitals. Because when we hybridize orbitals, we end up with the same number of orbitals that we had before. And there's only 1 s orbital in a level, so we can never have more than 1 s. And if you just have the s, you're not hybridizing anything, right? So you can have Sp, Sp2, or Sp3. Those are the only 3 possibilities. Okay? What's a little confusing is Sp2 looks a little bit like an electron configuration, right? And sometimes we would have electron configuration 1s2, well, let's change that. That's not going to work. 2s2, 2p2. And these 2 things kind of look similar, but they're different. Okay, this one has the valence shell numbers in them, or the principal energy levels, these principal quantum numbers, 2s, telling us which p orbitals these are. This doesn't have that. And so the only possibilities are Sp, Sp2, and Sp3. Those are the only 3 possibilities for hybridization. Any other questions?
So the answer would be Sp2.
For 36, the answer is Sp2. And you see there's this nice little line here. That's telling you write your answer on the line. Because when you're doing assignments like this, you want to make it easy for the person who's grading it. You don't want to have to make them search through, because they might not find your answer. right? And remember, I'm going to be looking through a big pile of these, and it's not my favorite activity. My favorite thing is teaching and explaining stuff to students and answering questions. Grading papers is real low. It's below cleaning the bathroom. So I'm not fond of it, so please make it as easy as possible.
So 37 would just be SP then, right?
37 would be SP, right? Because this carbon that they're pointing at has a double bond here and a double bond there, and so that fills its valence of needing 4 bonds. It can't have any hydrogens on it, so it's got 2. 2 would be SP.